Hi, I'm Rich with insideHPC. We're here at ISC'13 in Leipzig, Germany. And we're here at the nCore HPC booth, and I'm here with Ian. You are the founder of the company here?
I am.
That's right. Okay, so what are you showing here at ISC?
We're showing an ARM and DSP heterogeneous computer that is composed of a single node with 4 A15 ARM cores and 24 TI C'66 DSP cores with 26 gigabytes of ECC memory.
So what's this about? Is this all about green computing with the ARM?
It's about green computing with the ARM, but also the DSP brings some very unique performance characteristics. It has exceptionally low power consumption given the amount of compute that it's capable of doing. The other interesting thing about this computer is that the interconnect network is a non-traditional network that comes from the embedded computing space. It's called Serial Rapid I/O. It's got much less power consumption than Ethernet or InfiniBand, much better latency than either one, and the interconnect itself has better performance and also better message delivery capabilities than either InfiniBand or Ethernet.
So it came from the embedded space, like for like cell phone tower switches and
yes,
this kind of thing.
That's exactly right.
It's just set it up and it doesn't break, and
it's very reliable. It doesn't break. Almost every 3G and 4G phone call in the entire world is going over a Serial Rapid I/O network. Not to mention that NASA has just chosen it for the next generation Space Systems Interconnect.
Okay, so it has some speed as well.
It has some speed as well.
Okay.
So in our system, we're using each node is connected by a 20 gigabit bidirectional, non-blocking, point-to-point RDMA system, and on top of that you have OpenMPI.
So traditional programming tools, you could just get up.
You can use traditional programming tools such as OpenMP with accelerator model to offload compute to the DSPs, and between nodes you use OpenMPI. So it's the standard stuff that all HPC guys are looking for, and it's fairly easy to get your code onto this machine.
Okay, does this thing boot Linux?
It boots Linux. So it will parallel boot Linux. There's a specialized kernel that's created for the SoC, and otherwise you get a ARM, basically the ARM distribution for Ubuntu. You can use apt-get to install repositories. Otherwise, there's all the programming tools that you would traditionally expect.
Okay. All right. So at this stage, you've got this thing, and you plugged it into a chassis that actually existed for embedded devices.
This is correct. This is a COTS chassis. It's a standard called an ATCA. It's used in telecom and infrastructure all over the world. Mm-hmm. It's a PIC-MIG standard, and it's all of the technologies we're using here are COTS. So we were able to bring this computer to market very quickly using available hardware and silicon.
Sure. So you were able to, they had set form factors, and you just built it to that established standard.
That's correct.
And you could slide it in, right?
Yeah.
Okay. So what about the architecture here? They've got 3 processors. This is interesting.
We have 3 processors, and the reason why we do this is because we wanted to make sure that the ratio of ARM processors to DSP processors was correct, and also that ratio to the communication was correct. So we've chosen to use 3 TI. It's two generations of TI processors. It's the Keystone 1 and Keystone 2. Yeah. So the Keystone 2 is here. It has 4 ARM cores and 8 66X DSP cores, and then we use 2 Keystone 1 connected via hyperlink, and those also have the exact same DSP cores on them.
Okay, but they don't have the ARM. They're just there for.
They're just DSP. They're there for compute. That's exactly
fast throughput, right?
But from the programmer's perspective, it would be treated as 3 separate blocks of compute capability.
Okay. So this form factor, can we see what it looks like? What the card looks like here?
So this is a standard AMC form factor card. The final node for this particular computer will have 2 boards. This is the base board here with the 66AK2H12. That's 4 ARM cores and 8 DSP cores. We'll have a mezzanine board here, and you get to the mezzanine board via this high-speed C-Ray connector. On the mezzanine board, we'll have 2 C6678 Keystone 1 parts, and each one has 8 cores. So the entire module is about 45 watts. You get 4 A15 cores, you get 24 DSP cores, and 26 gigabytes of ECC memory. The interconnect on coming off this guy here is 1 gig Ethernet, 10 gig Ethernet, and serial rapid I/O. That's 20 gigabits, bidirectional, non-blocking point-to-point RDMA with 100 nanosecond switch latency. So it's very small, it's hot swappable. You can pull this card out and the system will continue to go. You can put it back in and the system will start back up again.
Oh, terrific.
Yep.
Well,
so it takes advantage of all the reliability and all of the maintainability of a telecom system, and you get that for you can take advantage of all of that for high performance computing.
Okay, so a lot of interesting aspects, but the bottom line is this might be an ideal kind of system for something like the Green 500.
That's correct, the Green 500.
Okay.
One of the interesting aspects of this system that we've built in for our top line customers is the ability to instrument every single power rail on this system with an A to D converter. And you can do experiments of compute versus power consumption. So we have 5 clocking networks on board this card, and you can trigger these clocking networks in a way that you can say, I've executed this instruction in the DSP, and I want to know simultaneously how much power I'm consuming in every aspect of the board, and the onboard telemetry system will allow you to do this.
So like if you were, like somebody from Barcelona or something was like trying to figure out where is the energy getting spent, they could get that instrumentation.
Yeah, that's exactly right.
Okay.
Once the hardware designers have taken their best shot at reducing power consumption with component selection and chassis selection and system integration, it's then up to the programmers to see what they're doing with their algorithm to really use the power on the board. And they can use this system to do those kinds of experiments and get extremely accurate numbers for power consumption.
Well, that's awesome. Well, you're a startup in HPC.
That's
so
right.
Congratulations.
Thank you very much.
We need to see more of this. So
thank you.
Good job.
I appreciate it.
You bet. Good job. Okay.